Good afternoon, everyone, and welcome to the Parsons Technical Webinar Series. I'm your host, Jessica Bennett. Today, we have Billy Baum with us, presenting on using drones to supplement characterization at complex sites. A few housekeeping items up front. Next slide, please. We'll be keeping all phone lines muted until the Q&A session at the end. If you have any questions throughout the presentation, you can either enter them in the chat feature at any time and we'll answer them at the end, or you can wait until the Q&A session and ask your question live. This webinar has been approved for 1 PDH credit. If you'd like to receive that professional development credit, you can download the form that you will have to fill out with your basic information. And there are also 4 multiple choice questions on that form that you'll have to complete. We'll also be entering the questions into the chat a couple times throughout the webinar. If you have any issues accessing that form, please let us know and send us an email and we'll get that to you. And finally, this webinar is being recorded and will be available on the Parsons YouTube channel in about a week or so. Next slide, please. So a brief agenda, I'll introduce our speaker, followed by a core value moment, the technical presentation, and then we'll wrap up at the end with Q&A. Billy is a senior munitions response geophysicist at Parsons. He specializes in collecting and interpreting digital and advanced geophysical classification data for federal clients such as the Army Corps of Engineers and NAVFAC. He has a bachelor's in geology from University of Colorado Boulder and has been with Parsons for over 7 years at this point. And with that, I'll turn it over to Billy for the core value moment.
All right, thanks for the introduction, Jessica. So presented here are Parsons' 6 core values. They're safety, quality, integrity, diversity, innovation, and sustainability. We start each installment of this technical webinar series with a core value moment focusing on one of these values. The content of today's webinar will relate back to several of these core values, but for today's core value moment, we'll be focusing on safety. Here at Parsons, we pride ourselves on safety, and we are committed to maintaining safe and healthy workplace environments and work practices for our employees, clients, and partners. Safety is a priority company-wide and is especially relevant for our many field projects that take place in challenging and unpredictable environments. So relating back to safety, slips, trips, and falls are one of the leading causes of preventable workplace injuries. Slips, trips, and falls are a special concern when working at environmental cleanup sites like munitions response sites, where field personnel are carrying and operating heavy or cumbersome equipment over rough terrain like steep slopes, loose soil, rocky ground, or snowy and slippery surfaces. Here at Parsons, we are constantly updating safety plans and reviewing best practices and tips to prevent falls. Some of the top tips we've come up with recently are listed here. The number 1 tip we have is to avoid hurrying or rushing. It's always important to pay close attention to your footing, to use proper footwear, and to eliminate distractions when walking on uneven surfaces. These tips don't just apply to hiking around in the wilderness, but are also useful in our everyday lives. And while casual walking seems like a simple or mundane everyday task, it's been a leading cause of preventable workplace injuries across all industries for many years. So getting started here, what are drones? So surely everyone here is somewhat familiar with drones. We see them often in everyday life and pop culture. Just last, my home city of Lakewood, Colorado, put on a fascinating synchronized drone show in place of the typical 4th of July fireworks show. But just to recap for everybody, drones are unmanned aircraft systems that are remotely operated by pilots that are not on board the aircraft. There are many different types and classes of drones tailored for many industries, anywhere from recreational toys to commercial applications and military combat weapons. Generally, commercial and industrial applications employ multi-rotor, small unmanned aircraft systems like the ones shown on the slide here. And the rest of this presentation will focus on these multi-rotor small unmanned aircraft systems, also referred to as SUAS. So the commercial applications of drones are widespread and include many industries. Some of the more common applications are listed here and include photography and videography, magnetometry, thermal imaging, light detection and ranging, or LiDAR, water sampling, methane detection, and inspection of landfills and construction sites. The range, stability, and precision of drones are extremely helpful for site characterization applications where site conditions may be complex. Drones can carry a wide range of payloads, including a long list of specialized characterization sensors, and mounting sensors to drones and deploying them aerially helps save time, cut costs, and improve safety for work crews. Parsons has been using drones for digitally enabled mappings, inspections, and environmental monitoring at challenging sites for several years now. The Parsons deployed its drone program in 2016, and it has been growing ever since. Last year in 2022, we completed 950 sorties or flights with over 210 hours in the air across 37 US states and Canadian provinces. Some of our most notable non-munitions related projects include roof and pipeline inspections and orphaned well detection. And then on the munitions response side of the house, Parsons has successfully implemented drone surveys to help characterize 6 sites over the past 2 years, with several more sites on our upcoming project schedule. Parsons currently has 25 active FAA licensed drone operators or pilots and a pool of over 50 licensed but currently inactive individuals. And typically at any one time, we maintain an active fleet of 15 drones of different manufacturers, models, each capable of deploying a wide range of payloads that are customizable for mission-specific objectives. And as technologies evolve and client needs change over time, we are able to add new drones with new capabilities to our fleet and move older or less capable drones into inactive status. In the next year, we are expecting to add several more drones and pilots to our active fleet to help meet our growing client needs for drone support. But before we get started here, I want to invite you all to join us on September 13th when Ron Kroshik and Sam Kermis will present another innovative drone project that Parsons is currently leading. Their presentation, Drones for Orphan Wells, Applying Modern Solutions to a Centuries-Old Problem, will cover how Parsons is using innovative technologies to aid in locating orphaned wells via drone-mounted magnetometers and other customized payloads. If you're interested in another unique application of a drone-based sensor, you should plan to attend that webinar again on September 13th. The focus of my presentation today is how Parsons is using drone-based technologies to supplement military munitions characterizations at formerly used defense sites. I'll be specifically focusing on a munitions response project being conducted under the Department of Defense's Military Munitions Response Program, or the MMRP, in accordance with the guidelines and regulations set forth in the Environmental Protection Agency's Comprehensive Environmental Response, Compensation, and Liability Act, or CERCLA. The Department of Defense's Military Munitions Response Program addresses munitions-related concerns from unexploded ordnance and munitions and explosives of concern at formerly used defense sites, also known as FUDs. Developed in 2001, the MMRP program prioritizes sites for characterization and cleanup based on the risk to human health and the environment from Department of Defense generated munitions-related hazards. As of September of 2021, the U.S. Army Corps of Engineers estimates that about 3,800 sites have been investigated or remediated to date, which leaves about 1,600 more to be addressed at that time. CERCLA, which is commonly known as the Superfund Act of 1980, provides funding for cleanup activities at a wide range of contaminated, including FUD sites. And the DoD's MMRP program follows the CERCLA cleanup process, which includes 7 general steps: the preliminary assessment and site inspection, the site characterization, the feasibility study, the proposed plan and record of decision, remedial design and remedial action, followed by completion and long-term monitoring. So in the next part of this presentation, we'll be focusing on an ongoing Parsons project that is currently in the 2nd and 3rd steps of the CERCLA process, the site characterization and feasibility study stage. And now time for the case study of the Hurricane Mesa test site. The Hurricane Mesa test site is located in southern Utah, approximately 150 miles northeast of Las Vegas, Nevada, and 15 miles west of Zion National Park, just outside of St. George, Utah. The site is part of a larger facility that has been known as the Hurricane Mesa Supersonic Research Site and the Hurricane Mesa Test Facility since the 1950s. It has been used by several military agencies and civilian contractors since 1955 and is still being operated today by a Department of Defense contractor called Collins Aerospace. Historically, the main use of this site has been to conduct supersonic aircraft escape system testing along a 12,000-foot sled track. The sled track itself is pictured here at the bottom right, and an example of an ejection system test run, complete with a crash test dummy being ejected from a mock cockpit, can be seen on top. There is also a history of live fire military munition training activities over the years. The 60 millimeter mortar at the left here is a live unexploded munition that we recovered from the site. This military munitions training use is what qualifies the Hurricane Mesa test site as a FUDS eligible site and makes it eligible for remediation under the MMRP program and CERCLA. 3,500 acres of the Hurricane Mesa Supersonic Research Site are considered FUDS eligible. The FUDS eligible boundary is shown here on the figure in blue. In 2020, Parsons was contracted by the U.S. Army Corps of Engineers to conduct a remedial investigation and feasibility study, also known as an RIFS, at a 1,368-acre munitions response site, shown here in yellow. The goals of the remedial investigation and feasibility study are to characterize the nature and extent of contamination by munitions and explosives of concern, or MEC, from DoD-related activities, and to assess risks to human health and environment due to the presence of munitions-related contamination, and to conduct a feasibility study to evaluate the costs and the practicality of proposed remedial activities, and to propose a plan for upcoming site remedies. Remediating the site or removing all munitions from the site is not a project objective during this RIFS phase. So when we sat down to look at the site and develop a technical approach for completing this remedial investigation, we quickly realized that the site was very complex, with severe terrain and a wide range of DoD uses, a wide range of current public land use and public interest due to its proximity to Zion National Park. So before we get started on the Hurricane Mesa site, I'll go over what a typical geophysical investigation looks like during an RIFS project at a FUD site. The remedial investigation phase of the CERCLA cleanup process for sites contaminated with military munitions generally implement geophysical surveys as the primary investigation method to characterize the types of munitions present and the aerial extent of the munitions contamination. Typically, remedial investigations for MMRP projects at FUD sites consist of a two-phased approach, where the first phase involves widespread geophysical surveys to identify the areas most likely to contain munitions-related contamination, followed by a focused geophysical investigation to identify and characterize discrete geophysical anomalies that are potentially indicative of individual subsurface munitions or munitions-related contamination. The sample area on the left here is a 1,500-acre bombing range in Florida that was sampled using widespread geophysical transects spaced from 177 meters to 350 meters apart. The geophysical results are displayed as a colored contour map where purple indicates the absence of metallic anomalies and red indicates the highest concentration of anomalies. Compiling the widespread geophysical results into a contour map like this helps us identify the areas of the highest concentration of munitions-related contamination are. In this example, you can see that the center of this range contains the highest concentration of anomalies, which is expected for a bombing target. Once we've produced this density analysis, we can pick locations to conduct focused high-density area characterizations. These focused characterizations are completed in grids that would be strategically placed within the highest density areas. The area on the right is an example of one of these high density area characterization grids. The one in this example is 1/4 acre. The subsurface metallic anomalies potentially indicative of munitions or munitions related contamination are shown in pink. The next step after collecting this geophysical data would be to intrusively investigate these anomalies to determine whether they are munitions or not. Also pictured throughout this slide are examples of the many types and deployable configurations of geophysical sensors that are commonly used during these types of investigations. And as you can see, the majority of them are fairly large and heavy, with some even requiring tow vehicles or skid steers to deploy them. And the main thing to take away here is that all of these sensors are best operated on flat ground. So first, before we can design the technical approach for the completion of the RI at Hurricane Mesa, we must understand what types of munitions and munitions-related contamination are expected to be present at the site. We'll tailor our geophysical characterization approach for each site based on the known and expected contamination profile. At Hurricane Mesa, we have two main categories of contamination. We have military munitions in the form of mortars, rockets, and grenades. And we have aircraft escape system test components in the form of rockets and jet-assisted takeoff components. So most of us are familiar with these military munitions as concepts, but the JATO may be new. So JATOs are more or less external rocket motors that can be affixed to an aircraft to help provide extra thrust during takeoff. They are typically ejected from the aircraft after takeoff, but can still contain explosive hazards even after ejected. The JATOs and rockets that were found at Hurricane Mesa would have been affixed to a rocket-propelled sled, which helped propel that sled down the sled track to get up to supersonic speeds before testing the function of their ejection systems. You can see here some JATOs affixed to the side of this rocket. So as is the standard for most MMRP RIFS projects, Parsons designed and implemented the two-phased terrestrial geophysical survey approach for characterizing the site, following the same typical geophysical survey structure described a few slides back. In phase one, we performed a preliminary characterization using widespread geophysical surveys to locate metallic anomalies and identified two areas with high metallic anomaly density, which helped us focus our phase two follow-on characterization investigations on those two areas. In phase two, We performed focused geophysical investigations within those two identified high-density areas to identify and characterize anomalies potentially indicative of individual munitions, and intrusively investigated them to determine whether they were munitions and munitions related or non-munitions related. In this figure, the results of the phase 1 surveys are shown as a colored density contour map, and the selected location for the phase 2 characterization survey grids are represented by the pink boxes. But what about this area in the center here with no data? Well, this gap in the geophysical data corresponds to cliffs and steep slopes that surround Hurricane Mesa. The vertical relief around the mesa ranges anywhere from 1,500 to 3,000 feet from the top of the mesa to the valley floor, which makes a significant portion of the site inaccessible to personnel, which in turn means it is not surveyable using the geophysical techniques that we use to investigate the accessible portions of the site. So the biggest challenge for us at Hurricane Mesa was dealing with this inaccessible terrain. For terrestrial geophysical surveys, we generally set the cutoff for what we consider feasible and safe to access at 30-degree slope. Here, about 500 acres of the site, or 36%, contain slopes that are greater than 30 degrees, and thus make them unsafe and infeasible to survey using the geophysical methods that we implemented for the rest of the site. So in years or decades past, this type of inaccessible area might just be ignored or considered a data gap to be dealt with at some point in the future or during some other project. But for this particular project and site, ignoring these areas was not an option for us. So we have a question: how do we investigate and characterize portions of a site that we can't access? So no surprise here, the answer is drones. During the planning phase for this project, we were already well aware of the amount of inaccessible terrain that we would encounter within the project area, so we had already come up with a plan. We designed a two-phased aerial characterization approach using drones, modeled after the two-phased geophysical approach that we used to characterize the accessible portions of the site. In phase 1, we would perform widespread drone-based photogrammetry surveys across the inaccessible areas to locate munitions-related contamination on the ground surface using 4K resolution photography in the visible spectrum. And we would identify and select areas with elevated densities of munitions-related contamination, or HD areas, for focused munitions characterization surveys during the second phase. And then in phase 2, we would conduct additional photogrammetry surveys over the HD areas that we identified. And phase 2 would include thermal imaging surveys to identify munitions-related contamination that may not have been identifiable in the visible spectrum imagery from phase 1. And then we use that characterization data to evaluate the nature and extent of munitions contamination across the inaccessible portions of the site, and thus fill in the data gap left after the geophysical investigation. Pictured here on the slide are some action shots of several drones that we used during the phase 1 and phase 2 surveys here. So during our preliminary aerial characterization phase 1, we collected 673 acres worth of photogrammetry data across our 500-acre inaccessible area, which included some overlap with our accessible areas. The drone's flight paths were pre-planned using drone deploy software to maximize coverage across the area and minimize the amount of flight time that we would need to get full and overlapping coverage of the entire area. In total, we recorded around 37,000 4K quality images and compiled them into photo mosaics so that they could be analyzed as one composite image rather than 37,000 individual photos. An analyst reviewed the composite images and identified over 800 non-natural or man-made items, including things like building debris, trash, wrecked cars, motorcycle parts, and even several bowling balls. And of course, what we were really after, 151 potentially munitions-related items, which included rockets, grenades, and JATO components. Due to the inaccessible terrain, we were not able to send unexploded ordnance specialists to inspect these items or to confirm whether they were truly munitions or not. So thus, we are forced at this point to refer to them as potentially munitions related. Pictured here is our drone pilot, Brett Lyons, who flew all of these missions for us. So here's some examples of the photogrammetry data that we collected. On the left of the screen, you can see some jet-assisted takeoff components. These are clearly identifiable in the 4K imagery, especially when you zoom in. And then on the right is a simplified diagram showing how we combined individual photos together to make the photo mosaic at the bottom. Once the photo mosaic was created, the data analyst brought it into ArcGIS, where they were able to zoom and pan around while they scanned it, looking for non-natural or man-made items. As they identified non-natural or munitions-related items, they logged the location and type of each item into a GIS database to keep track of the findings. In addition to the photogrammetry data, we also collected elevation modeling data to create a sub-meter accurate digital surface model. A digital surface model has a couple benefits. The first is that it gives us a better understanding of the terrain than the typically publicly available elevation data sets that can be found online. And second is that it gives us a much more accurate data set to use when planning our phase 2 flights. For reference, the publicly available elevation model that we used to plan the phase 1 surveys was a 5-meter resolute model, which was only resolute enough to let us fly our drone surveys at a minimum of 100-foot elevation. But the surface model that we created on our own using our elevation data derived from this digital surface model allowed us to fly our phase 2 drone surveys at a minimum of 65 feet elevation above ground. And the graphics here on the slide are the actual 3D and 2D representations of that digital surface model. So this figure presents the results of the phase 1 preliminary characterization survey. The 151 potentially munitions-related items that I discussed before are depicted here in red, while 749 non-munitions-related items are depicted in other colors. The vast majority of the potentially munitions-related items that we encountered were either rockets or JATO bottles, as well as some 40-millimeter grenades. The blue line on the figure depicts the proposed locations for our phase 2 focused aerial characterization surveys, which I'll elaborate here on some upcoming slides. And then the elevation data from our digital surface model is shown underneath on the green low to red high scale. Also worth noting on this figure are the black dots that can be seen around the lower edge of the collection area. These black dots are the location of munitions simulants that we placed across the site to test the performance of our preliminary surveys by ensuring that the simulants were detectable using our photogrammetry technology. I'll be discussing this process of seeding the site with munitions simulants later on again in this presentation. So next, we took the recorded locations of the potential munitions items and contoured them to estimate the density of the potential munitions across the inaccessible area and to identify areas with high potential munition densities. 2 high density areas were identified. Both are shown here in green on the figure. One on the cliffs at the end of the sled track in the center, and one on the cliffs just below the historical firing point just to the north. We then used a combination of the potential munitions finding database, the digital surface model, and this density analysis to plan our phase 2 characterization surveys. And those phase 2 surveys were planned to traverse the location of the potential munitions items identified during phase 1 and to include tighter spaced transect coverage over the HD areas identified on the figure here, and to follow the elevation contours that we calculated with our digital surface model. So then in phase 2, we collected about 16 miles of focused aerial characterization data along the transects that were presented on the phase 1 results map. For these surveys, we simultaneously collected photogrammetry in the visible spectrum and thermal emissivity data. In total, we collected about 30,000 images, 15,000 each in the visible and thermal spectrums. Before we started the phase 2 surveys, we did some testing to evaluate the relative thermal emissivity of different materials compared to the emissivity of the native soil at the site. The majority of the munitions expected to be present at this site were made of either aluminum or steel. So we created this test bed here on the left, which contained several types, sizes, and grades of aluminum and steel pipes. As you can see, the aluminum simulants show up clearly in the thermal data, while the steel simulants are a bit harder to see. Following the test flights, we placed about 30 aluminum and steel simulants across the site to monitor their detectability during the phase 2 photogrammetry and thermal surveys. And the picture on the right here is one of the steel simulants that we placed and successfully detected in both spectrums. You can see that this steel simulant shows up a little bit better during our survey than the steel simulants we used in our test bed. And as I mentioned earlier, we simultaneously collected that visible and thermal spectrum imagery, which means we have matching photos in both spectrums that we can compare against each other. Again, during phase 2, a data analyst reviewed the collected imagery to identify potential munitions items. However, this time the photos were not compiled into a photo mosaic and instead were reviewed as side-by-sides so that the analyst could review the visible and thermal spectrum image pairs together. At this scale, it's hard to pick out individual items, so I'll help you out. So as you can see here, the area on the top had several potentially munitions related items, and the area on the bottom just had one. And you can see how those stand out in the thermal imagery compared to the visible spectrum imagery. So using this method, we identified 50 additional potential munitions items in the visible spectrum that were not initially identified during phase 1. And 119 potential munitions items were identified out of the thermal imagery. The types and locations of these potential munitions were added to the database containing the potential munitions findings from phase 1. So here's some examples of different types of munitions and how they look in the visible and thermal spectrums. The table here shows that highly emissive materials like steel give off a very bright white signature, like the JATO bottle on the left, and less emissive materials like aluminum give off a dark black signature, like this rocket in the center. The two most common potential munitions items that we found were JATO bottles and rockets. Both give off a very strong thermal signature relative to the native soil at the site. And so both were very easy to identify in the data. It is noteworthy, however, that the 40 millimeter grenade casings that are clearly visible in our visible spectrum photography are not identifiable in the thermal data, which doesn't necessarily mean that all 40 millimeter grenades are not identifiable using thermal imaging. It just suggests that at the time of this survey, their thermal emissivity was too similar to the emissivity of the native soil for them to stand out. And some closing thoughts here on the performance of the visible and thermal spectrum imaging surveys. Materials on the high end and the low end of the thermal emissivity spectrum are easy to spot in thermal imagery, while materials with emissivities similar to the native soil are harder to see in thermal imageries. In general, the visible spectrum imagery was much more reliable for detecting the wide range and types of munitions present at Hurricane Mesa, but this may not be the case at another site where the background soil has a different emissivity than what we had at Hurricane Mesa. And a quick recap of the phase 2 characterization results shows that we identified 50 new potentially munitions related items in our visible spectrum imagery and 119 potentially munitions related items in our thermal imagery. So between both phase 1 and 2, a total of 201 individual potential munitions related items and 2 high density areas were identified. And I'll also note that all 119 munitions related items that we identified in our thermal imaging were also identified in the visible spectrum imagery. So those 119 are not counted against the total of 201. So as with any field project, we faced some challenges along the way. The first challenge related to the placement of the munitions simulants across the site. The project regulators required us to place simulants throughout our collection area to monitor the performance of our surveys. The problem with that was that our collection area was initially restricted to only include the inaccessible portions of the site. So we had to increase our planned survey area to include overlap with our accessible area so that we could access them to place the munitions simulants. This increased our collection area from 500 acres to 673 acres. The second challenge is related to weather. As with any type of drone work, flights are at the mercy of weather. We got pretty lucky and didn't lose too much time to weather here at Hurricane Mesa, but we did have to constantly be conscious of changing weather conditions and plan our surveys around weather events and optimal sun and cloud conditions. And the third and fourth challenges are both related to data processing and management. So processing this data was very time consuming. It took over 300 hours of combined computing and manual analysis. Many of the commercially available drone processing software programs are either fairly new or unreliable and can get buggy given the sheer number of images that we were running through it. And data management itself is challenging due to the enormous size of the data files. 4K quality images and the photo mosaics were very, very large files. Our final data package ended up being approximately 3 terabytes. So the main focus of the drone surveys at Hurricane Mesa were to investigate and characterize the inaccessible areas, but we also implemented drone surveys to help us collect secondary data over the accessible portions of the site that we characterized using geophysical methods. There are 4 main ways that we can use drones to supplement munitions characterization efforts at sites where inaccessible terrain is not an issue or is less of an issue than was here at Hurricane Mesa. We can develop vegetation density models to better understand the quantities and distribution of vegetation across the site. We can develop digital surface models to better understand terrain, topography, and extent of inaccessible areas. We can identify surface features, including target features like berms, craters, trenches, and scarring. And we can identify munitions-related surface contamination in areas where terrestrial surveys are not permitted. So in the case of the Hurricane Mesa, once we had completed our drone-based aerial characterization of our inaccessible steep areas, we move the drone operation over to 2 areas with confirmed munitions contamination in the accessible portion of the site. And these are areas where we used geophysical methods to confirm that contamination. Since we had already determined that these areas were contaminated, we wanted to use drones to help us figure out more about their physical characteristics. So we collected approximately 100 acres of visible spectrum 4K photogrammetry between the 2 areas and used that data to create a vegetation density model for each area. The results of our vegetation density analysis show us that about 25% of the area on the left was vegetated and 22% of the area in the middle was vegetated. We also use that photogrammetry data to create digital surface models over the 2 areas identified to help us better understand what the terrain was like within them. The digital surface models that we created show us that about 8% of the first area on the left was inaccessible and about 40% of the second area in the center was inaccessible. And the elevation data that we can get from the digital surface model is actually resolute enough that we can identify surface features like pits, berms, scars, and craters. In this example, the digital surface model brought out a surface depression that we could not see in the visible spectrum imagery. We identified this feature early enough on in our data processing effort that we still had crews at the site that we could send to investigate. When they went to investigate, they found a large depression about 15 feet in diameter and 2 to 3 feet deep. We decided to intrusively investigate that depression, and we ended up finding 7 live munitions items with a mix of mortars and grenades. This was able to help us identify this surface feature as a munitions disposal pit. So now that we've collected this secondary data over areas that we already knew were contaminated with munitions, what do we do with it? So the next step in the CERCLA process after the remedial investigation is the feasibility study. Here is where we identify remedial actions to clean up the site, estimate the cost to implement them, and the practicality or feasibility of completing them. This secondary data will prove useful in all 3 steps of the feasibility study. The vegetation density model helps us estimate the level of effort and costs of any vegetation removal that may be required prior to a follow-on cleanup activity, or in some cases where vegetation removal may be prohibited, it might help us identify remedial alternatives that can be implemented without disturbing that vegetation. The digital surface model can help us identify features like inaccessible terrain and identify remedial alternatives that are site appropriate based on terrain limitations. We can also use the identification of surface features like the pit from Hurricane Mesa to choose remedial alternatives that will address different types and natures of contaminations potentially present at a site. So up to this point, we've been looking at the technologies and methods that we implemented at the Hurricane Mesa site. And in this next section, we'll be looking forward to some new technologies that we're starting to implement and will continue implementing in projects going forward. And before we move on, I want to reiterate that one of our big challenges that we faced at Hurricane Mesa was the time that it took to process and analyze the photogrammetry data. A big factor in that is that we had a data analyst manually reviewing all of the data and hand picking the potential munitions items out of the photos. So the emerging technology that I'll be focusing on now is artificial intelligence and machine learning. So as I have alluded, manual data review was slow and expensive. And while it wasn't an issue at Hurricane Mesa specifically, manual data reviews can be unreliable or irrepeatable between analysts. And so most of us are generally familiar with artificial intelligence and machine learning as concepts. I am admittedly not an expert on either one, so I won't try to get into too much detail on the theory here, but implementing these technologies can help us become faster and more efficient at analyzing all types of data, including imagery data, by replacing or assisting the human element in that process. So some of the available technologies that we're starting to implement in our data analysis efforts are computer vision, object detection and recognition, and edge detection. And these are technologies where we can train artificial intelligence systems to be able to analyze photography data and identify potential munitions items based on characteristics like pixel color, geometry, identifying contiguous shapes, and recognizing patterns. So here's an example from a different project where we were tasked with identifying air-to-ground bombing targets from aircraft collected LiDAR data. For reference, this site is more than 160 times larger than the Hurricane Mesa site, which makes it virtually impossible to investigate and analyze without using some type of artificial intelligence assistance. At this site, Parsons developed a proprietary AI system that was able to identify over 385,000 surface depressions, and then using a series of decision rules that we fed it, was able to pare down that list from 385,000 to only 571 likely bomb crater locations. So this type of AI technology was specifically designed to use LiDAR elevation data, but it can be modified to run on photogrammetry data like the visible and thermal spectrum imagery that we collected at Hurricane Mesa. Now we'll move on to some closing thoughts and conclusions. So we've covered a lot of information thus far, and before we move on to a Q&A period, I'll summarize what we've gone through today. Traditional terrestrial geophysical investigation techniques for military munitions response program projects at formerly used defense sites are typically limited to terrain with less than 30-degree slopes. At the Hurricane Mesa test site in Utah, approximately 36% of the investigation area was inaccessible due to steep slopes and cliffs, so Parsons deployed drones to collect aerial photogrammetry and thermal imaging data in place of the traditional geophysical investigations. Analysis of that drone data identified 201 potentially munitions-related items on the surface and aided in the identification and delineation of 2 areas with elevated potential munitions densities. The use of these drone-based technologies enabled Parsons to create a full site characterization of the potential munitions contamination without producing any data gaps associated with the steep and inaccessible terrain. And looking forward, Parsons plans to continue using artificial intelligence and machine learning to more quickly and efficiently analyze visible spectrum imagery, thermal spectrum imagery, and other types of drone collected data. And lastly, I would like to give a special thanks to several colleagues and client partners listed here who made the Hurricane Mesa drone surveys a success and who helped me develop the content that was presented here today. We have 2 partners from the U.S. Army Corps of Engineers, Ms. Carrie Nelson and Mr. Kyle Lindsay. And then from my team here at Parsons, Ms. Carrie Ross, Mr. Brett Lyons, Mr. Daryl Hall, Mr. Nick Valentour, and Mr. Jeffrey Hong. And with that, it looks like we still have some time for questions. So I'll turn it over to Jessica to lead us through that.
Yeah, thank you.
Thank
Really,
you.
it was a great presentation on how drones can be used to address some really challenging sites to characterize them. I see there's quite a few questions in the chat, and a couple people have their hands raised. You can do either one, either raise your hand or enter it in the chat, and we will read it out or call on you. So to kick it off, the first question is, what are the geophysical techniques used for the non-sloped / challenging areas?
So we used we used digital geophysical mapping for our phase 1 surveys to help us identify the high density areas within our accessible terrain. And then we came back and used advanced geophysical classification to do our phase 2 HD area characterization. So the specific instruments that we used during phase 1 was the Parsons proprietary metal detector called a PDM8. And then during phase 2, we used DAGCAP validated advanced geophysical sensors, the Metal Mapper 2x2 and the Man Portable Vector. Not sure if that answers the question or not, but I hope it does.
Yeah, if any follow-up is needed from anyone who entered a question in the chat, just let us know. The next question is, was there an optimum time of day to perform the phase 2 thermal imaging? I'm assuming the metal objects absorbing and retaining heat, different than rock or sand, was used to distinguish anomalies.
Yeah, so we primarily planned our flights around sun angles, which of course correspond to times of day. For the thermal surveys, the main goal was to capture our thermal imagery as the metallic items were heating up, but before the rest of the soil and surrounding rocks had a chance to heat up as well. It was pretty difficult to plan this survey around that because of the complexity of the mesa. So it was definitely um, a well-planned effort in order to be able to collect that data, at the optimal sun angles times of day.
Okay, I see there's a few people with their hand raised. Salman Adalal, if you can unmute yourself, you can please ask your question.
Hi, can you hear me?
Yes.
Hi, I'm Salman. I'm a civil engineer calling from Bahrain.
Hello.
Hello, yes. I have a question. You've done a survey on the ammunitions found on the surface, yeah? Would it be possible to use the drones in some way to look for ammunitions found a bit deeper in the soil? Thank you.
Yeah. Yeah, thank you for the question. Yeah, so here at Hurricane Mesa, our goal was only to identify munitions on the surface, but there are other sites where identifying subsurface munitions using drones is an objective. On sites like that, we can use drone-mounted magnetometers and other types of metal detectors. Generally, sites that are flat are ideal for that type of technology because we have to dangle a magnetometer below a drone and then fly that drone at a constant elevation above the ground. So here at Hurricane Mesa, our terrain was far too complex for us to be able to hang a magnetometer off the drone and follow the contours at a constant elevation. But that is
Oh,
a technology that is used. And for those of you who are familiar with demining industries, that is one of the main technologies that they're using there.
thank you. Thank you very much.
Yep.
Okay, I see Max Bilinga. You have your hand raised. If you can unmute yourself and ask your question.
Yeah, I know you mentioned some names for the software that you use, but I was wondering what types of software that use to help plan your missions and process data, and how they work.
Yeah, so most of our missions were planned using a drone deploy software. And then when we got to the data processing, we used a combination of Pix 4D Mapper and Matic software. Those softwares were basically used to compile the photography data and help us geolocate each image. And then once we had the output from those softwares, we brought the photogrammetry data and the mosaics into ArcGIS, and we used ArcGIS to do the actual visual scanning of the photos.
Okay, great. Thank you.
Yep.
Okay, jumping back to questions that are in the chat. Was there consideration to perform nighttime flights to improve the thermal emissivity of the artificial objects?
Yes, so we did consider nighttime flights. At a FUD site and a project under the Military Munitions Response Program, night work can be tricky. There are a lot of hurdles that we have to jump through, mostly safety related. And so for this project, it was determined that we were going to stick to only daytime flights just to avoid that extra added hurdle. But that is a consideration on a lot of sites, and especially other industries that aren't being regulated by the MMRP and CERCLA programs. Thank you.
Okay, next question is, what type of accuracy did you achieve with your photogrammetry survey? How precise would you say that your logged locations for munition items or other targets would be?
Yeah, that's a great question. So all of our photogrammetry and thermal surveys were paired with centimeter accurate RTK quality GPS. So I didn't mention this in the presentation, but before we flew any of our missions, we went around the site and placed ground control points. These ground control points were measured with the centimeter accurate RTK GPS. And then during the pre-processing of the data, we were able to assign coordinates to each ground control point and then georeference each photo to that point. So our average root mean square positioning error was less than 10 centimeters, which means that we could return back to this site and find all of these items again with about 10 centimeter accuracy.
Okay, we've got one more question in the chat right now. How long does a typical flight last? I know one of the limiting factors right now for the use of drones is poor battery life and limited flight time. Did you have to make any modification to your drones or use special accessories to increase flight times?
Yeah, so our flight times here at Hurricane Mesa lasted on average about 20 minutes per flight, and ranged anywhere from 15 to maybe 25 minutes or so. We designed all of our missions to be on the conservative side to make sure that we would have time to get the drone back home safely without risking the batteries running out prematurely. We also planned our surveys to take place during the cooler fall and spring months. So thicker air and cooler temperatures gives the drone a little bit better performance, which helps battery life. As far as modifications or accessories, there's not many modifications that you can make, but accessories, we had a lot of spare batteries on hand. We also kept a portable generator at our staging and takeoff area where we were able to charge spare batteries while the drone was in flight. So we actually got pretty good production and quick turnaround times on swapping batteries, quickly in between flights. And as drone technology advances, the battery technology is advancing as well, and we're starting to see, better battery life and better flight times, as new drones come out.
Next question is, have we looked into hyperspectral or ultraviolet imaging?
Yeah, so when we first started planning these flights, we looked at a wide range of technologies that we could use. We ended up settling on the visible spectrum and the thermal technologies because we had prior experience using them, and didn't want to get too ahead of ourselves implementing a new technology at a site this complicated. There are other groups within Parsons that use drones for other applications, and they're the ones sort of more on the forefront of using those types of technologies.
Okay, and I see we've got Matt Vetter has his hand raised. If you can go ahead and ask your question.
Sure, thanks. Just a question. The one area you identified some disposal pits just based on the imagery that was kind of in the flatter areas. I was just wondering if anything was used similar in the inaccessible areas to try to identify any munitions that may have been buried just from either erosion or embedding themselves into the edge of the mesa.
Yeah, so we reviewed the digital surface model data for the steep sloped area the same way we did in the more accessible area, and we weren't able to identify any depressions that we felt were potentially indicative of munitions related contamination. And again, the slopes and the cliffs at this site were so severe that it would have been really difficult to identify a individual feature like that in that area.
Okay, well, I think we are at our time for today. If we can go to the next slide real quick. So our next webinar will be on August 16th, presented by Tim Ulte on constructing a virtual world, the benefits of digital twins and how to build them. So we hope you can join us for that webinar next month. Thank you again to everybody who joined us today and for all the excellent questions, and we hope to see you again next month.